A familiar part of the French landscape, it is now conquering distant territories in Africa and beyond. We take it for granted, but the TGV almost didn't see the light of day.
For long-distance travel, no one gave the train a chance.
While old modes of transport were being discarded in the post-war boom, the potential for train travel seemed boundless.
In the 1960s, a French engineer was offering amazing speeds of 300 to 400 kilometers per hour, which is unreal.
Meanwhile, the engineers developing the first TGV high-speed train were wrestling with a complex, real-world challenge.
We wondered whether we were being too optimistic. Would we be able to operate at 260 or 270 kilometers per hour?
How did the TGV revolutionize rail travel for a world hungry for speed?
It was a kind of revolution. In Europe, nothing quite like it had been seen on the tracks.
On the very first day, there were 75,000 passengers.
What innovations in engineering, track design, and route planning came together to ensure the TGV's success?
If you go too fast around a tight bend, you'll go off at a tangent.
While TGV is one of the safest high-speed lines in the world, accidents can happen.
The driver had just enough time to apply the brakes, but it was too late.
Although France has been spared in passenger-related tragedies, other countries aren't as fortunate.
A storm had caused the signaling and control systems to fail.
As one of the best-performing trains on Earth and holder of the world rail speed record, the TGV runs circles around its competitors at over 600 kilometers per hour.
The underlying principle is a magnetic field creating a blade between the locomotive and the rail.
In the fiercely competitive international high-speed market, TGV has continued to evolve, with the latest model offering a more streamlined profile. Now, 3D animation and interviews with experts are your first-class ticket to experience the exciting technological and human stories that propelled this trailblazing train, the TGV. This is high-speed rail's latest offering. After many years of hush-hush design, the new silhouette is finally revealed. Behind the elegant and sleek new profile lurks a host of technological innovations.
The aim of this project was to get a head start on the competition. There are many factors in which this TGV offers very significant progress. It is a train that will mark its era.
The Alstom plant in eastern France. This is where the pieces of a highly strategic puzzle are manufactured and assembled. The engine for the new TGV. It is 4 meters shorter compared to the previous generation, but just as powerful. And much more streamlined to allow considerable energy savings. 20% less than the TGV duplex.
20% is huge. It's a real breakthrough. We worked on a range of parameters to achieve this reduction. 2/3 of this is achieved through the train's aerodynamics.
We have experienced high-speed campaigns from recent years to incorporate all the know-how into this TGV and produce a train that is pretty efficient from an aerodynamic point of view.
This translates into a nose with an atypical shape. We worked on the bogie fairings and the fairing of the pantograph zone. A lot of tweaks on the right and on the left to produce an improvement in aerodynamic drag.
Over to the west, 800 kilometers away, is the Alstom site. The first engines manufactured in the East were taken across France to be assembled with the carriages manufactured in the La Rochelle workshops. With powertrains and carriages in tandem, like an athlete made of metal and stuffed full of electronics, it is ready for its first training sessions.
We're starting to assemble the first prototypes, for example, full-scale trains that will enable us to carry out static tests in the first instance, followed by a series of dynamic tests over a period of 18 months on the very high-speed networks.
Before 2024, the year of the commercial launch, the prototype must be assessed in a wide range of tests. The new TGV is pushed to its limits, being subjected, for example, to Sahara-type temperatures to test its air conditioning. Comfort, performance, safety. Everything needs to be scrutinized and approved before it is allowed to run with passengers on board. Meanwhile, production continues. 115 trains are to be delivered to the SNCF, which has decided to call its new model the TGV-M, M for modular.
This is the first TGV on which we can put 7, 8, or 9 carriages. Our old TGVs had a fixed number of 8. Here we can put the first or second class carriages and can easily transform one into the other. In terms of passenger space, we put in seats, but if we want to add luggage compartments or bicycle spaces, these are the same fixing points, so the train's configuration can be changed quickly and easily.
The 9-carriage train gives TGV-M a significant leap in capacity, with a potential 740 seats, which translates to 20% more passengers, all with reduced fuel consumption. Further major advances have been made with the tens of thousands of parts and cables that make up the innards of the train, all of which have the potential to fail. In the new TGV, every part will be continuously monitored by sensors, which send information via artificial intelligence to maintenance services.
On existing TGVs, we carry out what we call preventative maintenance. That is to say, we know that a component will last for 8 years. So after 8 years, all the train components are changed. Predictive maintenance disregards the projected lifespan of a component. The use of sensors produces physical and electrical readings that allow the beginnings of anomalies to be detected before the equipment actually fails. In first-generation trains, people came to the depot with USB keys to assess the health of the train. But with the later trains, we had daily data readings. Now we can transmit gigabytes of data 10 times a second. This potential is already being widely exploited in the aeronautics industry, but it is still being developed in the train industry.
Maintenance, energy consumption, capacity, modularity. A wide range of innovations is on offer, some of which are confidential trade secrets, as is the case with the new component that will be part of the architecture of the new trains. With the TGV-M, Alstom and the French National Railway Company seem to have optimized the TGV's industrial heritage to the full. It's a fascinating technological history that spans many decades. Why, in the mid-1960s, did only a handful of diehards believe in the future of high-speed rail? How did the TGV come into being in a world that considered the train a relic of the past?
Back in the 1960s, governments all over the world were in love with motorways and jet aircraft.
Trains were on the way out, except for regional services, particularly trains serving the greater suburbs. But for long distances, everyone thought that the train was doomed to obsolescence.
While the whole world was contemplating the end of long-distance train travel, Japan proved the naysayers wrong, developing the first high-speed train, the Shinkansen.
When the first part opened between Tokyo and Osaka in 1964, It was a real railway revolution. Trains were running at 210 kilometers an hour, much faster than anywhere else in the world.
2 years after the Japanese Shinkansen was put into service, the French railway company tentatively set up a research department to develop a high-speed train project.
The SNCF research department had 75 people. At that time, the equivalent research department for Japanese trains had 1,000 workers.
At the time this department was set up, French trains ran at an average speed of 160 kilometers per hour. One benchmark the handful of high-speed researchers could look to was the SNCF's flagship model, the Capitole. This train had been running between Paris and the southwest of France at speeds of up to 200 kilometers per hour since 1967, but that was widely regarded as the top speed for any locomotive.
At the time, every country in the world was convinced that pretty much the ultimate speed for railways was somewhere in the 200 kilometers an hour range, and that any improvements would mean doing things differently. Hence, the development of the German and Japanese magnetic levitation systems.
In France, people remembered the world record of 1955.
320, 325. The figures on the speedometer are impressive.
The SNCF, though, decided to focus on developing existing rail technology rather than the magnetic levitation train.
In 1955, 2 locomotives were accelerated up to the amazing speed of 326 and 331 kilometers an hour. And so French engineers knew that trains could run much faster, so there was lots of potential.
One of the ways to increase speed was to use trains equipped with turbines that run not on electricity, but rather oil. More powerful, lighter, less expensive to run, able to reach speeds of 225 kilometers per hour, these trains inspired the future TGV.
These were the famous turbo trains that ran on the line between Paris and France's Atlantic coast. They were hugely successful. They were so fast, they were known as the teacher turbos, in reference to teachers who lived in Paris and taught in Normandy.
What was needed was a train with independent traction, since it was less expensive than an electric train, with the attendant line electrification. So the idea was to do something really new by harnessing the kind of technologies used in aeronautics.
For the TGV, the biggest development borrowed from aeronautics was turbine technology.
Researchers turned to helicopter turbines. There was no new turbine specifically designed for the TGV-001.
The same turbines that equipped record-breaking military helicopters in the 1960s.
The idea was to equip high-speed trains with aeronautical turbines, whose lightness gives a very high power density. The first experimental train was equipped with 4 turbines. At a little more than 4,000 kilowatts, it had more power than existing locomotives.
Fueled by a mixture of gas and kerosene, the turbines drove an alternator to create an electric current. The current, in turn, powered the traction motors located in the train's wheel systems, called bogies.
None of the parts operate on reciprocating movement, whereas in a diesel engine you have cylinders with pistons that wear out, crankshafts knocking, etc. This was beautiful. It was going to be something really extraordinary.
March 23, 1972. Something exceptional rolled out of the Alstom workshops, codename TGV-001. TGV for Turbotrain à grande vitesse. Its shape was revolutionary. This was light years away from the design of the then running locomotives.
The search for higher speeds forced us to address the issue of resistance to forward motion. You don't need to be an expert in aerodynamics to grasp that the cube-shaped locomotive is problematic. So we put it through the wind tunnel and found the ideal profile for 300 kilometers per hour.
This is the first time we've seen a profile with a slightly longer nose. It was more streamlined compared to previous locomotives. So from an aerodynamic point of view, it really was revolutionary.
This completely redesigned aerodynamic design was the work of a man from a completely different world, automobile designer Jacques Couper.
We brought in someone who had designed sports cars. We tried to adopt any good ideas, including those from outside the world of rail travel, which was a relatively new direction. And that's how we came up with the TGV-001.
We needed a train with a dynamic, powerful shape, given that it would be traveling at speeds of around 300 kilometers per hour. We have a luggage compartment at the rear because in this train, passengers cannot keep large luggage with them. They have to put it in the hold.
The TGV developed at the time was modeled on an aircraft cabin, and, as in aeronautics, the engineers sought weight reductions wherever possible. Polyester laminate fairings, aluminum bulkheads, plastic air conditioning ducts. Everything was designed to that end. One area where the weight saving was considerable is the wheel system. The bogies were now located between the carriages.
The 5 carriages were coupled together to make a fixed-form train. This was a revolution.
Bogies were usually placed beneath carriages with symmetrically arranged units. In these high-speed trains, for the first time, the bogies were placed between rather than beneath the carriages, with the help of an intercirculation ring. Fewer bogies means a lighter train, one that is both less expensive to produce and more aerodynamic.
An articulated train has the advantage of having far fewer bogies, which are areas of turbulence, strongly contributing to aerodynamic drag, creating forces that work against the train's progress.
Boasting this new kind of aerodynamics, testing for the turbotrain à grande vitesse began on the rail network. From the very earliest trials, it reached speeds far in excess of those achieved by the Capitole and even the Shinkansen.
The first test runs were in eastern France, the region around the plant where the train was assembled. We quickly reached 260 kilometers per hour, which was the commercial objective. But we were soon close to 300 kilometers per hour, which was absolutely extraordinary.
With the TGV, the French National Railway Company now had a champion to restore its image. Except that after a few months of testing, clocking up tens of thousands of kilometers, one component of the train was beginning to worry the engineers.
In November 1972, at 240 kilometers per hour, instabilities were noticed in the bogie, which began making irrepressible movements.
If you push a shopping cart a little too fast and the caster is not well adjusted, it can start to judder. The same can happen with a high-speed train bogie.
We wondered whether we were being over-optimistic. Could we really run trains at 260 or 270 kilometers per hour?
While the SNCF was sweating it out with its prototype, it suddenly had to deal with an outsider, appearing as if from nowhere. With its futuristic shape, it made a big impression.
In the 1960s, a French engineer came up with a project called the Aerotrain. The proposed speeds of 300 to 400 kilometers per hour were completely surreal at the time.
The TGV-001 was beaten to the punch by the Aerotrain in terms of speed, which in 1969 had already reached a speed of 422 kilometers per hour. What were the pros and cons of the two projects that were getting the transport industry so excited? Why did the Aerotrain manage to seduce so many decision makers to the extent of overshadowing the TGV?
The Aerotrain was an outstanding project and rather visionary.
There is no question that the Aerotrain gave us a challenge.
This is Jean Bertrand. the man who pushed the SNCF out of the spotlight in the mid-60s.
No component is in contact with the track. The machine can go at any speed.
A brilliant graduate of the prestigious engineering school Polytechnique, he filed several patents for the aeronautics industry.
Jean Bertrand, a great engineer, had the idea of developing an air-cushioned train.
While a new mode of transport, the aerotrain did not reinvent the wheel. On the contrary, it dispensed with it altogether.
It is a train for which the support functions are air cushions, meaning the body of the vehicle reposes on air cushions inflated with air. A very small jet of air maintains the required pressure. Transversal guidance is handled by vertical cushions enclosed around a concrete rail.
The infrastructure is a monorail in the shape of an inverted T, about 10 meters high. To propel the machine, 2 turbines drive a propeller more than 2 meters 40 in diameter. And to brake, Bertrand used the design adopted by a number of aircraft, harnessing reverse thrust affected by changing the orientation of the blades.
The aerotrain is very simple, and that's why it was such a great idea.
The first prototypes came out of Jean Bertrand's workshop in the early 1960s, with many improvements incorporated thereafter. While the design was indeed brilliant, the concept had a number of weaknesses right from the outset. In fact, the aerotrain was like inventing a car that goes much faster than any other, but cannot be driven on highways.
The major problem was that it necessitated the building of completely new infrastructures. It was not compatible with boarding in some Paris train stations. Imagine a viaduct running from Paris to Marseille, with a terminal in Paris on a concrete viaduct. This would be absolutely unthinkable. The aerotrain had another disadvantage. It needed to be turned around. Turning one unit around is fine. You can do it in a single turntable, but when you have 5, it's another matter.
Unlike the aerotrain, the turbotrain à grande vitesse could run in both directions and pull into any station on the conventional existing rail network. Moreover, in terms of capacity, the two technologies were leagues apart.
You have to consider that a TGV has 500 seats. With 2 of them together, you can have more than 1,000 seats. This was a vehicle with 80 seats, so economically, it was a very expensive line for a really poor capacity.
Not only did the aerotrain carry fewer passengers, it also consumed more energy.
Maintaining the air pressure to ensure lift and guidance, even at a standstill, consumes a lot of energy.
Despite its obvious drawbacks, the aerotrain eclipsed the TGV, and the futuristic project had the attentive ear of the public authorities.
It enjoyed a novelty appeal and excellent lobbying, fueling the enthusiasm of well-placed people in government circles.
The TGV was a development entirely financed by the SNCF, whereas the aerotrain was backed by the public authorities.
The aerotrain had the ear of the government of the day because a good government is one that innovates. This was an era of gargantuan ventures, of progress, of the unprecedented.
The speed performance of the aerotrain was so impressive that the government signed a contract with Jean Bertrand to build a line in the Paris region running between the suburbs and the capital's business district. The future for the aerotrain seemed bright. Then in 1974, the contract was suddenly canceled. What prompted this U-turn by the government of the day? A few months earlier, in the fall of 1973, oil prices began to soar.
With the oil crisis in 1973, the price per barrel increased 4-fold. For railways, which have diesel locomotives, the impact was only 4%. But for cars, it was 40 to 50%, and for aircraft, around 70 to 80% of the cost.
The gas-guzzling aerotrain fell from grace as the wind turned in favor of the SNCF. At one of his last cabinet meetings, the French president at the time validated the project for a high-speed line between Paris and Lyon, a decision made easier by his belief that the TGV-001 would run not on gas turbines, but on electricity.
When Roger Guibert, the chairman of SNCF, presented the Paris-Lyon high-speed line project, Pompidou said to Guibert, "By the way, your train is electric, right?" Guibert paused for a moment and said, "Why, yes, Mr. President." The next day, he told his engineers, "Well, guys, we got it all wrong. It has to be electric."
Although the SNCF and Alstom had won the industrial battle with the aerotrain, they now had to roll up their sleeves to produce a train compatible with the new economic reality.
This wasn't in the plans at all. Everything had to be refitted, but that's what saved the TGV. It was electric.
While the new TGV was based on the architecture of the turbotrain à grande vitesse, the helicopter turbines had to be replaced by a more complex electrical system.
The drive engine of the TGV is still based on 4 major functional blocks. The first block captures the energy from the catenary via the pantograph. The second block acts as a transformer, reducing the 25 kilovolts of the catenary to a voltage of around 1000 volts. The third block is the electrical converters, which transform this catenary energy into energy and motor control. And the last block is the motor, with the kinematic chain that drives the axle.
While designing this new train, the engineers took the opportunity to solve the problem with the bogies, identified during testing for the TGV-001.
In a locomotive, the engine is simple. It's right in the bogie. For the TGV, to lighten the bogie, the engine was mounted into the body.
The commercial running speed for the new TGV was meant to be 260 kilometers per hour, and the first Paris-Lyon line was already planning 300 kilometers per hour. Carrying the train's empty weight of 350 tons along with passengers at such a speed requires a commensurate amount of power.
A train is like an electric coffee grinder. If you power your coffee grinder with 180 volts instead of 220, it will run a little slower. For a train to run at 300 or 320 kilometers per hour in service, it needs enough energy to run at that speed.
On a high-speed line, the TGV receives a current of 25,000 volts, compared to the 1,500 for a conventional line. The current is carried by a copper wire called the catenary. The energy is conveyed to the train via a jointed framework called a pantograph. This contact zone between the catenary and pantograph is a vital component.
Energy passes between pantograph and catenary through a surface area the size of a 1-pound coin.
As with conventional trains, the TGV's collector head running on the catenary is fixed at an angle. This creates a zigzag effect to prevent the catenary from always rubbing in the same place and sawing the pantograph head in two. In addition to the usual lateral movement, in the case of high-speed trains, vertical movement of the pantograph also had to be incorporated.
The catenary is rather like a vibrating rope, so you need a good match between the speed of the train and the speed of the wave. This is what we call critical speed of the catenary.
If incorrectly adjusted, the pantograph loses contact, causing arcing.
The faster you go, the higher the frequency of the oscillations, so the collector head needs to be very light. Hence, a 2-level pantograph was developed for the TGV.
The first level is sufficient for reduced speeds on the conventional network, when the TGV is leaving or entering a station, for example. The second level of the pantograph needs to be able to adjust to the much more rapid oscillations of the catenary on a high-speed line.
A small, light pantograph with improved contact with the catenary was a new development.
With its lighter bogies, new electric motor, and revised pantograph, the TGV was ready to roll. A few months before its launch, the SNCF began a communications blitz.
During my presentations on the equipment, I was often asked whether the TGV would have seatbelts. I realized we needed to show we had room for maneuver.
To show what it could do, the TGV challenged the legendary 1955 record. To that end, the SNCF chose a standard train set identical to all the other leaving the Alstom factories, only with slightly larger wheels and a more sophisticated gearing system. While the engineers knew perfectly well that they could easily exceed the 260 kilometers per hour, they still had to overcome the previous 331 kilometers per hour record.
Waiting for permission to depart.
Depart.
On February 26, 1981, the voltage was boosted to 29,000 volts. 3 carriages were taken away to lower the weight, and the speedster was pushed to its limits.
Pull, let's go.
The 1955 record was easily surpassed. With the media watching for the slightest slip-up, the TGV began clocking up the numbers, one after the other.
373, 74, 75, 76, 77, 78, 79, 380. We have reached 380 kilometers per hour.
At 381, we reduced the speed because the catenary was lifting. In France, it made the headlines. I remember the headline in the newspaper at the time, "The Fabulous TGV."
That demonstrated to other people in the railway, and particularly to the public, that running at really high speed was quite safe. There was a huge margin between the maximum commercial speed, which was 260 kilometers an hour, and just what had been achieved with this special test at 380.
On the strength of this new world record, the TGV Paris Southeast Line was inaugurated 7 months later amid much fanfare by the recently elected president, François Mitterrand. With its futuristic lines, the 200-meter-long orange snake was causing quite a stir both inside and outside the country.
It was a kind of revolution in Europe. Nothing quite like it had been seen on the tracks. The TGV train itself was full of innovations. It was quite lightweight, it had a low-slung body, and it had a lot of interesting equipment on it, like in-cab signaling, so the driver didn't have to look at any line-side signals.
The other thing that struck people was its color, orange. That was the designer's choice. It was the orange era. It became the color of progress. It was going to be very difficult to abandon it for the Atlantic network, which wanted to use blue.
With the introduction of the TGV, the journey time between Paris and Lyon was now just 2 hours and 40 minutes, compared to more than 4 hours previously. It was a colossal time saving and a big challenge to air travel, which had constantly been gaining market share in the 60s and 70s.
When the first TGV line was opened, the engineers said they were expecting 17,000 passengers a day. Are you sure? Don't be silly. Let's say 16,000. On the first day, there were 75,000 passengers.
It was an immediate commercial success. The price difference between the TGV and air travel was enormous. A TGV ticket cost 200 francs, while a plane ticket was around 800.
In 1981, French travelers were introduced not only to a new train and reservation system, but also to a revolutionary infrastructure. No freight trains. No conventional trains. This was the first line in Europe reserved for high-speed travel.
It was a massive project in so many respects. The first being civil engineering, hydraulic structures, earth structures, engineering structures, 13-meter platforms, layers and sublayers that needed to be absolutely perfect.
In setting up this first line, the engineers were able to take advantage of the TGV's principal trump card, its speed.
The Paris-Lyon line was a real breakthrough, inasmuch as with conventional heavy trains, it had previously been better to dig a tunnel or make a cutting, but the TGV's inertia allowed it to handle gradients, then use the descent to recover speed.
When you're in the cab at that speed, you can see that it's moving in all directions. A freight train couldn't climb the slope.
It was built with a lot of steep gradients, a kind of switchback, and this avoided the use of tunnels, which are very expensive, saving about 15% of the cost.
Although the TGV was capable of negotiating slopes of 3.5% compared to only 1% for conventional trains, it needed to avoid curves as much as possible.
The line layout had to be compatible with the speed, meaning the faster you go, the straighter you have to shoot.
You can't travel at 270 or 300 kilometers per hour with a small bend radius. If you go too fast around a tight bend, it's like riding a bicycle or driving a car. You'll skid and go off at a tangent. Simple mathematical formulas that show that every speed has a minimum bend radius. On high-speed trains, the smallest radii are something like 4,000 meters.
This radius can exceed 6,000 meters for lines running at 350 kilometers per hour. Such radii give the TGV a much higher margin of safety in terms of derailment. It could potentially go faster, but does not.
It's a question of passenger comfort. That's to say, we want passengers to be able to go to the bar and return with their drinks, etc., without falling and spilling them on other passengers. So this is what limits the train's speed in a bend.
Although built to be as rectilinear as possible, the line is much like a traditional track, only more so.
The engineers worked a lot on the ballast, which is made from pebbles. They not only used more of it, they also used very, very hard ballast that can withstand the effect of extremely strong dynamic loads.
Each sleeper weighs around 300 kilos, so they are very heavy, enough to drown in the ballast. They aim to move as little as possible.
On this base of volcanic rock and concrete, 432-meter-long rails are laid, making them 100 meters longer than the height of the Eiffel Tower.
The welded rail sections can be made extremely long. Also, the rail is heavy, weighing 60 kilograms per meter. For conventional lines, the weight is only 50 kilos.
In order to supply the TGV with power via the kilometers of copper wire in the catenaries, another colossal project involved the construction of electrical substations.
A substation is the end power outlet. This is the connection to the RTE network, the Electrical Energy Transport Network.
Each station transforms the 225,000 volts of the RTE network into 25,000 volts for use by the TGV, with substations required every 50 kilometers or so.
If the network strays too far from a substation, the current passing through the cables will weaken. So instead of having 25,000 volts, you might have, say, only 21,000 volts.
The first high-speed line was completed in 1983. Then in 1989 and 1990, the TGV was introduced in other towns near Paris. In 1993, it came to the north of France and the Channel Tunnel the following year. Provence and the French Riviera had to wait until 2001. Now, with more than 2,800 kilometers of high-speed lines, France has the fourth most extensive network in the world, after China, Spain, and Japan. In France and elsewhere, the network is constantly expanding all over the world.
There are projects in Eastern Europe, there are high-speed lines in Morocco and in Saudi Arabia, and there is a high-speed line under construction in California. I think there's a lot of potential for more high-speed lines.
High-speed rail travel is viewed in such a positive light because it offers so many benefits. Journey times are sometimes faster than air travel. It has a much better carbon footprint, and all this with an extremely high level of safety.
On dedicated high-speed lines, the railway is very safe. There are no level crossings, The signaling and train control is nearly always automated, so there is no human error. And if you look back over the history, there have only been 2 serious accidents.
What caused these deadliest accidents around the world? Why is TGV one of the safest trains in the world? What technological innovation has enabled it to avoid derailments? On January 30th, 2003, a TGV train traveling at more than 100 kilometers per hour collided with a heavy goods vehicle stuck on a level crossing. Only one axle came off the rails. The rest of the train remained on the track. December 21st, 1993, a train from the north of France to Paris flirted with disaster while traveling at 300 kilometers per hour.
The earth covering the remains of some First World War trenches collapsed. The TGV came through. The opening was several meters wide. But the track held firm. The train was not derailed.
Faced with such conditions, a conventional train would have crashed or derailed and concertinaed. But the TGV remained on the track. The secret of such resilience lies in a component that has existed since the birth of the very first train, the bogie. By changing the position of the bogies to make the train lighter, the TGV designers made the train more rigid without realizing it.
The articulated train has another advantage that we hadn't considered at all, which is that as a single block, a fixed-shaped snake, it can only be derailed with difficulty.
The articulated train set is a plus compared to conventional trains where carriages are connected by buffer couplings, which are much looser and break much more easily. An articulated train forms a kind of spine.
Despite being an articulated train, the TGV is not immune to accidents, although they remain relatively rare. One of the greatest fears for a TGV is the prospect of a head-on collision, especially on a conventional track, as happened in the French Alps in 1988.
A TGV was traveling on a conventional line at 110 kilometers an hour. Around a bend, a convoy was struck on a level crossing. The driver had just enough time to brake, but it was too late. The driver was killed, and the tragedy forced us into a rethink. It triggered all the modeling and crash tests carried out afterwards to produce a train that responded better to events external to the TGV system.
2015, Eastern France, this time on a high-speed line. This incident was the greatest tragedy to affect high-speed rail travel in France, but it did not involve a passenger service. A train being tested on the new TGV East line approached a bend too fast. A train left the tracks and ended up in a canal. 11 people died.
Unfortunately, we had a terrible accident with a train that was being tested, which means all the safety devices that monitor the speed of a commercial train had been deliberately bypassed for testing purposes.
While rare, fatal high-speed passenger accidents have occurred outside France. In Europe, the worst incident occurred in Germany in 1998 on the Munich-Hamburg line. An equipment failure at a wheel triggered a chain reaction that led to all the carriages being derailed. The accident killed 101 people and injured 88. In Asia, the Wenzhou disaster in 2011 killed 36 people and injured nearly 200, undermining confidence in the safety of the Chinese network.
A storm had caused the signaling and control systems to fail, and the staff decided to use manual control, and maybe they weren't as familiar with the procedures as they should have been, and it ended up with one train colliding with the rear of another, and it happened on the viaduct.
Since its inception, the The TGV has had a dozen or so accidents, but not a single life has been lost among the billions of passengers transported in all of its history. Along with the Japanese Shinkansen, it is the safest train in the world. Is that enough to guarantee export success? It's not that simple. Which countries have chosen to adopt the TGV? Who are the historical competitors and the new challengers? How does it manage to hold its own in an ultra-competitive market?
Today, 1 out of every 2 high-speed trains in the world is an Alstom train or one with the Alstom high-speed technology.
In 1990, the TGV passed the mythical 500 km/h mark and set a new record. Hitting a speed of 515 km/h, the iconic high-speed train astonished the world, winning over countries planning to launch a high-speed rail service. After Spain in 1992, it was South Korea's turn in 1994. And while the Spaniards only bought the actual train this time, South Korea took the whole TGV system.
There had been competition between the Japanese, the French, and the Germans, and the French won it, and part of the deal was that they would transfer their TGV technology to South Korea.
The Koreans chose the track technology, the signaling, and the Alstom train, so they really embraced TGV's technology in its entirety.
After 10 years of Franco-Korean cooperation, the KTX was launched in 2004. 6 years later, France was once again exporting its TGV system. Trains manufactured by Alstom were shipped and made their first trips along the Moroccan coastline in 2018.
Morocco had the first high-speed system in Africa, and it was French.
Infrastructure, signaling, maintenance services, TGV duplex. The entire TGV system was bought for the line between Tangiers and Casablanca. Winning a contract worth several billion euros was all the more satisfying in such a highly competitive niche market.
Who are the TGV's competitors? Well, aside from what you might call the historical competitors, the Germans with ICE and the Japanese with successive versions of their high-speed train, there were also new competitors, notably the Spanish.
In Spain, the Talgo company has high-speed trains which they exported to Saudi Arabia. So there's quite a lot of competition there.
Among the new players in high-speed rail, one in particular was developing rapidly: China.
The Chinese railways have built a huge network, about 40,000 kilometers, and the trains run at up to 350 kilometers an hour, the fastest in the world. Potentially, it is a huge competitor, but so far it has not succeeded in breaking into the markets which have been dominated by French, German, and Japanese suppliers.
For the time being, they are focused on domestic development. But it is very likely that they will be competing on the international markets one day soon.
In the global race for the faster high-speed land travel, one project that was thought to be dead and buried has been resurrected: the maglev. In Japan in 2015, it reached a record speed of 603 kilometers per hour, with the plan to link Tokyo to Nagoya in 40 minutes, meaning 286 kilometers at a speed of 500 kilometers per hour. It achieves such astonishing speeds thanks to magnetic levitation.
The principle is based on a magnetic field, creating a blade between the moving train and the rail, made from concrete in this case.
When the maglev gains speed, the wheels retract. The train levitates thanks to copper coils located in the side rails, which interact with magnets incorporated into the train. Propulsion is produced by other electromagnets on the sides of the train, interacting with another series of coils. The permanent inversion of north-south polarities makes the maglev move forward. While the technology is spectacular, like Jean Bertin's Aerotrain, it is not without certain drawbacks.
There is only one high-speed commercial maglev operation. That's in China, in Shanghai. The infrastructure involves using huge quantities of copper to generate the magnetic field. So that's a problem simply because of the cost.
Ignoring the significantly higher energy cost compared to the train, the main handicap of the maglev is its non-operability with existing networks.
The question of networks is a strategic issue, and some are reluctant to embark on the construction of high-speed lines. This is the case in England, Italy, Poland, and in the United States, on the flagship line between Boston and Washington, passing through New York and Philadelphia. Alstom managed to establish itself in the 1990s with a train that could reach high speeds on a conventional line. A contract was renewed in 2016 for a similar train in an improved version.
It's a potentially large market. We also know that there is a well-established and powerful air lobby, which is probably why it hasn't developed so much. The tilting train, as it is called, was a big factor in Alstom's success in winning this American market.
The tilting train is technically capable of leaning into bends, thus saving considerable time on winding routes.
It's a train where inclination is safely controlled according to the speed and the curve of the bend.
Using sensors and an onboard database, the train anticipates approaching bends. Once the information has been analyzed by the onboard computer, signals are sent to the mobile pantograph and to the bogies, which are tilted by means of cylinders. The system allows travelers to endure greater centrifugal force without feeling any motion sickness.
The advantage of the tilting train is that it allows you to go about 20 to 30% faster without having to rebuild the track.
With more modest speed targets, perhaps the rail industry is finally entering the age of reason. The latest model, the TGV-M, is capable of running at 350 kilometers per hour, but its main selling point is not that it goes faster, but that it is more fuel efficient.
I think it's come just at the right time because energy costs have spiraled up and lower costs for operating trains would be absolutely vital for the future.
The ecological challenge is a real opportunity for rail travel because it is the mode of public transport that offers the best carbon footprint.
Decades of know-how in high-speed rail travel has enabled SNCF and Alstom to perfect their trains, generation after generation. Their latest offering is better connected, more economical, and more environmentally friendly. A TGV in tune with the times. In the coming years, an unprecedented development of high-speed lines all over the world is expected, and the TGV may well be holding all the cards.
In some 40 years, it's transformed the French landscape. Its three-letter name becoming iconic in France, TGV. Traversing the country on nearly 3,000 kilometers of rails, the TGV has transported more than 3 billion travelers since it launched in 1981. During that time, it has constantly evolved with groundbreaking technology forever changing the future of train travel. Here comes the TGV-M.
For the TGV-M, we wanted to improve upon everything that made the TGVs a success.
What changes should we make to create something modern that reflects society today?
They came up with an ambitious list.
We chose 400 innovative ideas for the TGV-M.
It's a jewel of technology.
One impressive innovation is called a graft, which can reduce the train's dependence on the national power grid.
It's the only one like it in the world.
This improvement gives the TGV more reliability.
If an overhead line breaks, for example, the TGV-M can travel for tens of kilometers before it stops.
The TGV-M's standout feature isn't its speed. Nowadays, it breaks records for its low energy consumption, a whopping 20% less than the previous generation of trains.
20% is a lot. It's really groundbreaking.
How does it do it? partly because of its optimized aerodynamic profile.
The shape of the nose is completely different.
You can barely tell the difference between the locomotive and the cars.
While the silhouette has been transformed, the interior has had a makeover too.
This train will be quieter and have more natural light because there are 25% more windows.
Along with its new ergonomic seats, improved internet connection, and two-story bar car, the TGV-M will be able to carry more passengers.
Multiple trains hooked up to one another could carry up to 1,500 passengers at a time.
Not only can they carry more passengers, they're also more adaptable, unlike the old TGVs, which couldn't be modified at all.
The M stands for modular. A first-class car can be transformed into a second-class car and vice versa.
The M might also stand for maintenance, made simpler and more accurate with the help of hundreds of sensors connected to artificial intelligence.
There are sensors all over the train.
From the initial sketches of the TGV-M to its first run on the French rail network,
320 kilometers per hour is almost 100 meters per second. There's no margin for error.
with a peek behind the scenes to see how they're built and tested, combined with 3D animation, we'll tell the story of this extraordinary 10-year industrial venture that created this train. The embodiment of the future of high-speed travel in France and abroad. Now arriving, the TGV-M. No fewer than 10 industrial sites are involved in the production of the TGV-M. It was in Saint-Ouen, in the outskirts of Paris, that the silhouette of the new train first saw the light of day. It might seem surprising, but this technological treasure was born from a few strokes of a pencil.
We integrate the technical requirements as soon as possible, which means that we have to come up with some very innovative solutions. But we always start with a research phase. That research can be done with nothing more than a pencil and a pile of Post-its. That's how it starts.
The speed at which these sketches are being created belies the complexity of the task. For this new train, the designers had to come up with a worthy successor to the TGV Duplex, which broke world records by surpassing 574 kilometers per hour. The list of requirements for the TGV-M is long and ambitious. It also marks a first in the history of French rail. An innovation partnership between the SNCF, the traditional rail company and sponsor, and manufacturer, Alstom.
The competition had to catch up to our TGVs. We also had to get a head start on facing new challenges, such as global warming.
We wanted to drastically reduce what we call the global cost, which is to say the cost of acquisition for our clients, but also maintenance costs over the next 30 years and energy costs.
Another goal was to make the product more attractive by giving it a higher passenger capacity than the old TGV trains, and by adding equipment on board that would improve the customer experience.
The SNCF, for their part, wanted a TGV that would cost less, consume less, have a higher capacity, and be more comfortable and adaptable. A seemingly impossible equation with multiple unknowns. But luckily, they could depend on France's experience with high-speed rail travel.
The idea was to draw on the heritage of BB locomotives, namely their characteristic design and the panoramic aspect that was also found on the first TGV trains.
Today's design is a nod to the locomotives that once pulled capital trains between Paris and Toulouse, but it's also a symbol of a technological breakthrough that came about with the first TGVs. In the mid-1970s, when the first high-speed train in France was designed, it was well ahead of its time. It had to reach the commercial speed of 270 kilometers per hour, which was about 100 kilometers faster than most trains at the time. In order to achieve that goal, they had to revolutionize the traditional rectangular shape of locomotives.
They realized how much the shape affected the aerodynamics of the train, as the speed gradually increased to the 320 kilometers per hour we have today. There are around 4 meters between the very tip of the nose and the first wheel truck. You can barely tell the difference between the locomotive and the cars. It's all one continuous line that starts at the tip of the nose and continues straight through to the very back of the train.
In addition to breaking speed records, this new train also had an original architectural design. The bogies, or wheel trucks, were not attached in the usual way. Instead of having 2 sets of wheels under each car, they were placed between the cars, resulting in a smaller total number of wheels.
Reducing the number of wheel trucks meant less drag, and having a fairly rigid connection between the cars prevented any sort of wave-like movement. That resulted in a high-speed train set that was very stable in terms of railway dynamics.
The vocabulary of that first design was a complete break with the other trains that were being built at the time. It was very innovative and became a reference in high-speed transport.
The subsequent generations all maintained the principle of articulated cars, but gradually introduced improvements to performance, cost, comfort, and environmental impact. After the first TGV was put into service in 1981 in the form of the famous bright orange TGV Southeast, the second generation switched to a blue color scheme.
In the 1990s, the introduction of a second generation of trains meant that high-speed trains could be found all over France, on the Atlantic coast, in the north, everywhere.
Many small adjustments were made for the TGV Atlantic, especially the one-level version whose upper part was reworked.
The TGV Atlantic was put into service in 1989 and went from 8 to 10 cars and 380 to 480 seats. Most importantly, the train, weighing over 400 tons, could travel at 300 kilometers per hour.
In the mid-1990s, a third generation of TGVs was introduced in the form of double-deckers. High-speed rail travel was so successful that certain lines were starting to be saturated, so they had to increase the capacity of the trains.
The TGV Duplex was the first high-speed train in the world to have 2 levels. It was capable of carrying 520 travelers per train at a speed of 320 kilometers per hour. A 4th generation of high-speed trains, designed exclusively by Alstom for the European market, has never circulated in France. The AGV, or Automatrice à grande vitesse, which can travel at more than 350 kilometers per hour.
Alstom used what it had learned when designing other high-speed products, such as the AGV, which is used in Italy, taking the aerodynamic profile of those trains into consideration when coming up with a design for this new TGV.
Even more aerodynamic than the AGV, this is what the locomotive of the TGV-M looks like. What are the improvements, and why is it shaped the way it is?
What you need to know is that 60% of drag, which is a force that opposes the motion of the train, comes from the locomotive. So it's essential that we come up with some innovations that lead the vehicle. Modern industrial tools, technological progress, and our ability to produce more complex pieces means that we're capable of doing things we couldn't do before, or at least not without resulting in unreasonable production costs. Today, we have computing power and software that makes it possible for us to work on areas we didn't know how to work on in the past.
More modifications have been made for the TGV-M than were made for the TGV Duplex, with 2 goals in mind: to make it more efficient and to give it a distinctive look.
The shape of the nose is completely different. It's 1.5 meters longer than the old TGVs, which makes it more streamlined and enables it to pass through the air more easily.
We didn't want the shape to be boring. We wanted to give it character too, most notably on either side of the cabin, on what are known as the shoulders, which give the locomotive extra force and create an impression of controlled power.
On the central windshield, they removed the niches from the TGV Duplex, so the windshield is now flat. One major element of the lower part was also redesigned.
The first wheel truck is a weak point in terms of aerodynamics, so we streamlined it. It's an important innovation compared to the old TGVs.
Streamlining the first wheel truck is important because it simultaneously improves airflow and decreases noise pollution.
The undercarriage may have been streamlined, but another particularly sensitive zone was completely transformed. The alcove reserved for the pantograph, the arm that extends out from the top of the train to make electrical contact.
The pantograph area on the TGVs was kind of a mess in terms of aerodynamics. There was a lot of equipment on the roof. So one of the innovations for the TGV-M was to remove as much equipment as possible from the roof and integrate those systems into the inside of the locomotive to get a simpler rooftop.
A lot of work was done on the pantograph to make it as streamlined as possible. Once again, minimizing and diminishing the turbulence around this important piece of technology was key.
The pantograph and the wheel truck were streamlined, and the aerodynamic profile was improved, but the locomotive has even more secrets in store. Some of them are paramount because they allow the TGV-M to carry more passengers than before. To discover what's hiding behind this new silhouette, we must travel to the factory where they're assembling an incredible technological puzzle, a massive, completely redesigned structure.
The biggest difference is that instead of starting with the old generation and making improvements left and right, we really redesigned it from the ground up. We asked what changes we should make to create something modern that reflects society today.
It's here in Belfort, in eastern France, that Alstom is producing this new-age locomotive. On the same site where the first prototype of a high-speed French train, the historic TGV-001, was built in the 1970s. The first step in building the locomotive of the TGV-M here in Belfort was overseen by the R&D department after they received the designer's preliminary sketches.
Whenever we start a new project with the designers from Saint-Ouen, they present us with the sketches, and then we look at what's feasible or not. We went back and forth several times to figure out how we could make something that corresponded to what we wanted in terms of both design and aerodynamics.
That perfect balance of design and aerodynamics all begins with simple pieces of steel of all shapes and sizes, like this one here, that will make up one side of the locomotive.
The first step, which is sheet metal work, starts with unfinished pieces of sheet metal. There are a few parts that we buy pre-made, but mostly we just start with sheet metal that we cut out, fold, and then assemble into small subsections ourselves.
It takes more than 4,700 welding points to assemble this new locomotive, over 95% of which are done by hand. As the engine comes together, the small subsections become heavier and heavier, and more difficult to manipulate. When the large subsections are finally assembled, the skeleton of the locomotive is nearly complete. The metal must be heated up one more time, but not to be welded.
When you weld sheet metal, it causes a lot of deformation. It contracts, so we have to correct the sides to get them to be nice and even again.
Every measurement and every welding point must be checked before the locomotive is sent to the paint shop. 10 days later, the locomotive comes back out in immaculate shape. It's moved from station to station, where it's fitted out with the rest of its equipment in a very precise, choreographed dance.
The locomotive is kind of like a shoebox because it doesn't have a roof, but all the sides are closed. The rest of the equipment is put into place using bridge cranes. We're talking about blocks that are 3 meters long and weigh 3 tons that need to be put in exactly the right position. Once that's done, we can screw everything into place and connect the electrical wiring and plumbing. It will still have to be tested later, but that's really the step that makes the locomotive complete instead of just a steel structure.
Once it's fully equipped, this massive vehicle full of electronics weighs 50 tons. 10 tons more than an Airbus A320, and that's without the wheels. This locomotive is much higher tech than the previous generation, yet weighs nearly just as much to ensure good grip on the rails. The new locomotive is much smaller, however, even though it's more effective than ever. On the TGV duplex, all the functional blocks, including the transformer, were placed right in the middle of the locomotive. For this new design, they've been moved or reduced in size.
We redid the whole architecture of the locomotives in order to make them smaller. We changed how they're built. Instead of having two side corridors, there's just one central corridor, and the transformer is down below.
The transformer is used to reduce the voltage from the overhead lines from 25,000 volts down to 1,000 volts from the electrical equipment on board. Thanks to advances in technology, we've also been able to miniaturize the technical compartments. The third major innovation was to simplify the distribution of energy on board the train for systems that keep the passengers comfortable, such as their air conditioning. What was known as the common block on the old TGVs has been phased out, enabling us to reduce the size of the locomotive by 4 meters.
The fact that the new locomotive is 4 meters shorter than that of the TGV duplex results in an 8-meter reduction for the train overall. This changes the whole architecture of the French TGV, most notably with this new feature resembling a space capsule, which the designers of the TGV-M have baptized the graft. Why did they choose to use this medical term? What purpose does it serve? What makes it so revolutionary? To discover the secrets of this major innovation to the French high-speed train, we must travel to another Alstom factory, located 800 kilometers to the west, in Étré, near La Rochelle. To understand the primary purpose of the graft, we must take a look back at the previous generations of TGVs.
Right from the start, the basic idea behind the architecture of the TGVs was to have a locomotive on either side of a fixed train set in what was known as an articulated arrangement. The locomotives are independent vehicles. Each one has 2 wheel trucks. Each car shares a wheel truck, meaning that it stops in the middle of the wheel truck where the next one starts. The individual cars can't be connected on their own. If you want to add an extra car on the end, it has to be linked to the back of the locomotive.
In the designs for the TGV-M, one of the primary goals was to reduce production costs by standardizing the cars as much as possible for production in La Rochelle. Thanks to this graft, there's no longer any need to build a special car for the end of the train.
With the Euro duplex, we had 3 types of vehicles, which meant that there were 3 assembly lines. One for bar cars, one for the so-called intermediate cars, and one specifically for the cars at the end of the train. With the TGV-M, we have 2 production lines, one for bar cars, which is still different, and one for everything else. That's what we mean by standardization. At the end of the production cycle, we assemble the graft mechanically, which allows us to make the connection between the locomotive and
the graft has the same exterior shell as the regular cars and the same length of 3 meters. It serves the same purpose as the cars at the end did in the past, but with one additional advantage. It can carry the equipment that used to be located inside the locomotive or on the lower level of the bar car.
The graft is a new piece that we designed to store technical equipment. It contains all the energy storage equipment. The TGV-M is simpler than the older TGVs. They had 6 battery blocks, whereas the TGV-M has just 4, 2 per graft, to supply 110-volt power to the train.
But the benefits don't stop there, and its other features are even more surprising. In addition to the low-voltage batteries, the graft is also equipped to store energy in 700-volt batteries.
The energy storage feature is a new innovation for the TGV-M. Being able to store energy has several benefits, the first of which is keeping the passengers comfortable.
When there's an incident on the network that knocks out the power from the overhead lines, with our current TGVs, the air conditioning stops after 30 minutes. The lights dim, and the toilets are out of order. With the batteries, however, we can keep all those elements of passenger comfort running for 2 or 3 hours, which is long enough to deal with the technical problem.
Having batteries to store energy is good for more than just passenger comfort. Consider the hypothetical situation of losing power from the overhead lines once again. The TGV-M would be able to keep driving at a reduced speed of between 30 and 60 kilometers per hour.
The other advantage is that it can keep the train moving if the power from the overhead lines is knocked out during a storm, for example. The train can keep traveling for several kilometers.
That means the train might be able to reach a section of the rails with power or a garage where they could potentially transfer the passengers to another train. What's great about this graft is that it will allow us to clear the lines and resume regular traffic flow sooner after an incident on the network.
The last innovation enabled by the grafts on the TGV-M is that they make it possible to temporarily relieve stress on the national power grid by switching to energy from the batteries on board the train.
From time to time, we get alerts saying that the electrical consumption in France is higher than the means of production. Thanks to these batteries, we can reduce the amount of electricity the train is drawing from the power grid for an hour at a time. If we scale that up to 200 trains, it means eliminating an electrical consumption equivalent to that of a city of 50,000 people for 1 hour. That's a major innovation, and it's the first in the world.
Thanks to the graft, which is full of innovations, Alstom and the SNCF were able to come up with a standard car to be manufactured in the workshops near La Rochelle. With its brand new graft and mini locomotive, what will this new train look like? How did they manage to increase the space for passengers while simultaneously increasing passenger capacity? How has this train of the future been adapted for global warming?
The carbon footprint per passenger has significantly improved. It's 35 to 37% better than the old double-decker TGVs and 50% better than single-level TGVs.
The TGV cars take shape at the La Rochelle site. First, they create the shell of the vehicle, not out of steel like for the locomotive, but rather out of aluminium.
To make the shells of our train cars, we start with aluminum sections we receive from our suppliers. We take those aluminum sections and put them together. Then, to assemble them mechanically, we weld them. There are no rivets. Everything's welded.
The aluminium sheets are assembled primarily by robots, but a battalion of 80 welders work together to assemble the more complicated sections that would be too difficult or costly to weld robotically. Each shell has no less than 2.5 kilometers of welded joints. Once the welding is done, they must abrade certain sections to smooth out any swelling. And of course, another fundamental step consists in preparing the various pieces that will eventually contain the future equipment.
The aluminum sections we receive are unfinished. We cut the openings we need, such as windows, doors, and hatches, to access technical areas where the air conditioning and such will be stored. All of that's done on automated machining benches.
Once the shell is finished, the dimensions are analyzed using not a magnifying glass, but a laser.
It's not clock-making, but every millimeter counts when we're making our structures.
Once the measurements have been verified, the structure is sent to the paint shop for 12 days before being returned to the production floor using a transporter. Then it's time for the last step, fitting.
Fitting consists of equipping each vehicle in the train set with all the necessary amenities for both its basic functions and elements of passenger comfort, such as seats, windows, floors, and carpets. Everything the passengers see is put in place during the fitting stage. There are some 5,000 items on a single train, so you can imagine the number of different things that go into every one of these vehicles.
During this final stage, one particularly strategic step is to finish all the wiring.
There are a lot of wires in a vehicle because the train is connected. There's approximately 1 kilometer of cables per linear meter of train. So for a vehicle that's 17 meters long, we have 17 kilometers of wire.
For the new TGVs, the Étré site took the opportunity to review the production process. New tools were created to make it more rational and ergonomic, such as this wiring arm.
By the time the vehicle reaches the fitting stage, it's all been assembled, so we can't go in through the roof anymore, only through the ends. So we designed a telescopic arm that we can use to put the bundles into place, which are the length of the vehicle, reducing the time it takes to hook up all the wires.
The train cars may be made in La Rochelle, but their interior design comes from the Saint-Ouen site. The teams from Alstom have a precious tool at their disposal to confirm that design. A panoramic screen that allows them to envision the interior of the train before it's industrially produced.
We have a screen almost 3 meters tall and 6 meters long. It lets us see some very precise details, such as the space between the trains, the ends of the cars, and the doors. It shows the interior of the train to scale.
In immersive mode, the novelty of the new design becomes apparent.
One thing you barely notice because of the black stripe is the relative smallness of the window frames. The windows are slightly less tall to get more horizontal visibility.
The interior of the train was designed to be much more comfortable than before, starting with the seats. They're much more rounded, and the headrests can be adapted to different body shapes. In addition, each seat comes equipped with certain features that are indispensable today, such as an outlet. The train will also have an excellent Wi-Fi connection that's up to 5G standards. Finally, the train will be quieter and let in more natural light, because the TGV-M has 25% more windows than the previous TGV. We enlarged the windows in the passenger cars and added windows to the sections between cars on the upper level. We even added windows in the bathrooms, but obviously, these are one-way glass.
Not only are there more windows than before, but they were designed with global warming and increased sunshine in mind. They're more efficient, as is the air conditioning system, which helps reduce the energy consumption of the train.
We use new materials that provide better insulation, such as heat-resistant films that are applied to the windows so that the sunlight doesn't warm up the inside of the train car. Finally, the major change was to the air conditioning system. It adapts to the number of passengers in the car. If there are no passengers in the car, the cooling system will detect that and reduce its energy consumption as much as possible.
There have been numerous changes for passengers, but also for the train operators themselves. The letter M in its name is synonymous with a major transformation.
The M in TGV-M stands for modular. What that means is that a first-class car can be transformed into a second-class car and vice versa, relatively quickly, to adapt to seasonal variations in traffic. Much of the interior equipment can be replaced extremely fast. It's fairly easy to add more luggage racks or space to transport bicycles, for example. We can also remove luggage racks and storage space to make more room for passenger seating and such.
Thanks to a system of interior rails, each car can now be transformed as if it were made of Lego. But the modular aspect also applies to the train as a whole. The architecture of the train can be modified, whereas TGV duplexes always have the same 8 cars.
The TGV duplex is always the same. It's not modular at all, so that's really an innovation for the TGV-M, that idea of preserving the advantages of an articulated train set, but also introducing the idea of modularity, which means we can remove 1 or 2 cars so we can have the TGV-Ms with 7, 8, or 9 cars.
These changes were made possible by the size of the locomotive. The new design is just 18 meters long instead of 22, for a total saving of 8 meters for 2 locomotives. The reduced technical space of the cars also saved 1 meter per car, leaving enough space to add a 9th. Since the graft now carries equipment that used to be transported on the bar car, or passenger cars, those cars can now be removed without losing any important features. For the SNCF, this new TGV offers both greater flexibility and a higher passenger capacity.
The INWI version of the TGV-M will be able to carry up to 600 passengers, compared to just 509 or 550 passengers on the two-level TGVs we have today. The WeGo version will be able to transport up to 740 passengers, as opposed to just 630 today. That means that the two trains hooked up to one another could accommodate nearly 1,500 passengers at a time.
But there's still a lot of work to be done before these trains can start carrying passengers. There are numerous stages to the process, such as when the first locomotives manufactured in Belfort arrive in La Rochelle, so they can put together the first TGV-M train set.
The first time we put a whole train set together is always very symbolic, because it's the result of years of design work. It's the moment when the new train is born, and it marks the start of the testing phase, so it's really the beginning of the story.
A story in which the TGV-M will have to show what it's made of. To what kinds of trials will this new train be subjected? How will it be ramped up before the commercial launch? And why does the test phase take so long?
Roman for Dominique.
The time from putting together the first train set to the end of the project, when the train is approved for transport on the French rail network, is usually around 12 to 18 months. Our goal is to be able to do it in 12 months, which is a really big challenge.
The massive Alstom site near La Rochelle features a rather particular service where almost an entire train can be tested without actually having that train on hand. It's known as the Train Lab.
For the TGV-M, we invested a lot in the Train Lab so we could test out all of its features beforehand. By features, we mean the passenger entrance, where the passenger pushes a button to open the door and things like that. That's what we reproduce in the Train Lab for various physical elements, such as doors, wiring, windows, and computers, but also digital elements, such as models of the motor and other parts. It's a way for us to validate features and save time on development in order to get a train certified before it's actually been built.
It's like having a rough draft of the train before the first train set is actually completed. You can see it driving virtually here to test the passenger information display systems. This new tool, which has been used throughout the development and testing of the TGV-M, has already become very important.
For previous projects, between the moment when we assembled the first train set and the moment when we turned it on for the first time, it took 3 to 4 months. For this train, it took us 2 days. It saved us 3 or 4 months of checking for problems and searching every single wire of the 200 kilometers of wires inside this train. We saved very valuable time.
The Alstom teams have been developing this incredible tool since 2009. The first test bench was fairly limited in terms of capacity, but the modelling available today means that they can simulate, for example, all of the wiring in the entire train. Year after year, more and more digital features are being added.
Much of the train is digitized today, but we have to keep going until as much of it is digitized as possible, because it will save all of us time, both during the development and also once the train is up and running and ready to get certified and do trials on the rail network. We hope that as we continue testing this train and it keeps growing in maturity, this tool will remain helpful, because we won't have to do all our testing on the train itself. It will also optimize costs for us, because we won't have to use actual trains. We'd rather use our trains to carry passengers than for testing.
Despite the extensive digitization of the TGV-M, some physical testing is still required. One of the first tests takes place on the same site in Étré in what's called an environmental chamber. Sensors have been placed inside the cabin of the locomotive. Using heat lamps, it will be subjected to temperatures worthy of the Sahara Desert to test the cooling system's response.
We have sensors that measure the temperature and humidity levels to make sure the air conditioning is responding correctly to the extreme conditions to which we're subjecting the cabin. It's the same for the technical compartment, where we put sensors to measure the temperature, airflow, and humidity levels to ensure the air is circulating well enough to keep the engine block and electronics cool. That's the first thing we check. If there's a problem there, the train won't be able to travel at the speeds at which it's meant to travel.
The TGV-M hasn't been put into circulation yet, but it's already traveling across Europe. One of its destinations is Vienna, the capital of Austria. In another environmental chamber there, the French train will be pushed to its limits by recreating some even more extreme conditions.
A miniature section of the train set has been sent to Vienna to be tested in the environmental chamber of the Vienna Arsenal, which is unique in Europe. The trials we're doing there will be used to confirm and approve the climate control on board the train, but also another element that we can't test in Étré, which is the speed of the train. They can subject it to wind, snow, sun, and all sorts of other things there.
In Vienna, they can simulate wind speeds of up to 160 kilometers per hour to test the heating and insulation of the train cars, with some rather unusual passengers on board.
We simulate the presence of passengers by putting hot water bottles inside the cars. Those bottles are a certain temperature, which is the normal body temperature of humans, and they're placed beneath the seats to reproduce the energy put out by each passenger.
Once again, like with the anti-UV film placed on the windows, the designers of the TGV-M have taken climate change into account in their plans.
We measure the temperature and humidity in different parts of the car to see if the air is flowing as we expected, which is very important. If it's very hot at one end of the car and very cold at the other, that's no good, because everyone will be unhappy. So the car has to be prepared to go from minus 25 degrees Celsius with snow and frost, which are very detrimental to railways, to very hot temperatures. We subject the train to extreme temperatures in testing, because unfortunately, we know it can easily get up to 40 or 45 degrees in certain areas nowadays.
The trials in Étré and Vienna are mere warm-ups for this athlete that will one day have to travel Europe at 320 kilometers per hour. It will have to accelerate much more quickly than is possible in La Rochelle or Belfort. The train's first high-speed travel will take place not in France, but abroad in the Czech Republic. To be exact, on a site unlike any other in Europe, located 40 kilometers east of Prague, Velím.
Velím is a circuit where we can test the overall functioning of the train at speeds of up to 200 kilometers per hour. Velím is essential in getting the authorizations we need to put these trains into service on our network.
A legacy of the communist era, this site has two tracks, one nearly 4 kilometers long and another more than 13 kilometers long. It's the only circuit in Europe where trains can be tested at speeds of 200 kilometers per hour. This is essential because at this stage of its development, the TGV-M cannot run on the regular network without risk of disturbing commercial traffic. The only solution would be for it to run at times of day when the current TGVs are not on the tracks.
Basically, we would have to take a given line and shut it down, then run the train at night to try to make sure it's compatible. Today, we wouldn't have enough time to do that, and it would be very expensive to do it on the network.
The trains they use for the trials obviously don't look like normal trains. They're not equipped with seats or passengers. Instead, the travelers it will carry one day are represented by weights scattered all along the length of the train. Using wiring and monitors galore, the TGV-M will be examined from every angle, in hopes of finding a problem, as strange as that might sound.
We cannot drive a train at 320 kilometers per hour without first making sure it's safe at 150, 160, or 200 kilometers per hour. We start out very simply at 100 kilometers per hour to check the train's overall behavior. Then we ramp it up to 200 kilometers per hour and examine how the train responds in terms of electricity, stability, and any potential traffic safety issues. Velím is useful for that too, to highlight any areas that might be problematic, so that we can resolve any issues early on and avoid trouble once the train is in commercial service.
Alone on its circuit, the TGV-M will go around and around, travelling 15,000 kilometers over 6 months at all times of the day and in every kind of weather.
The test train will run 5 days of the week, day and night. In Velem, it gets down to -10 or -15 at night, and it snows. So we'll also be able to check how the train responds to snow in order to make sure the brakes function properly no matter the conditions. We'll put black soap on the tracks too, and then try braking on that specific section to reproduce the problem of wet leaves accumulating on the tracks in the fall.
By its second day at Velem, the test train has already been able to run at 200 kilometers per hour for 350 kilometers. None of the older generations of TGV trains reached this stage so early in their testing. Once all of the objectives have been met during these 6 months of testing, it'll be time for another important step in the TGV-M's history: driving at 320 kilometers per hour on the French rail network.
French people are used to traveling at 320 kilometers per hour, but it's really quite something. It's almost 100 meters per second. There's no margin for error.
Before attempting to hit 320 kilometers per hour, the TGV-M took its first steps in France on a section of tracks that were closed to traffic. It was an emotional moment for everyone.
Naturally, after so many months of preparation, when you see the trains start to move along the national rail network for the first time, it gives you goosebumps. It's a pretty incredible sight.
Inside its cabin, which was redesigned with the help of drivers, the TGV-M has begun to travel across France from west to east. Strangely, as you watch the tracks go by, the feeling of speed is less impressive than in the older TGVs.
I wouldn't call it trivial, because you still hear some of the same noises you used to, but it's much quieter and it's comfortable. It's like going from a classic car to something more luxurious. You don't have the same feeling of speed. That's what it's like traveling on the TGV-M.
Hidden away from prying eyes in the Alstom hangar in Belfort, the TGV-M is preparing to finally break the symbolic barrier of 320 kilometers per hour. Each new phase in testing starts with a briefing.
Latest update, I asked permission to boost the train.
The teams have scheduled every bit of testing down to the last second, but things always come up at the last minute. The last few days have had their fair share of surprises on the site chosen for these crucial tests. The Rhine-Rhône high-speed line between Belfort and Besançon.
All sorts of unexpected things can happen. A measurement chain can break and stop us in our tracks. The windshield wipers could stop working in the middle of a downpour. A truck could catch fire beneath the lifting platform the night before, preventing us from reaching the speeds we had been targeting. That's what testing is all about, dealing with a constant stream of problems.
The ability to improvise is all the more important as these trials are taking place amidst commercial traffic. Regular passengers will be travelling on the same tracks within minutes of the TGV-M.
This step is very important for our tests, of course, but we're working around commercial traffic. When something starts to go wrong, it can get in the way of commercial traffic, but it also throws off our own schedule. It puts more pressure on the team, and as soon as something comes up, we have to face it head on and talk to the right person right away to make sure it's handled quickly.
That day, after finding the source of a new technical issue and repairing it in record time, the testing team was finally able to drive the train at full speed, reaching and even surpassing the crucial target of 320 kilometers per hour.
Hitting 320 is a big turning point in the project because it's the speed at which the train will be traveling most of the time. The stakes are high because it will determine whether we will pass all the tests in order to put the train on the market.
320 kilometers might be crucial, but it's still just one step in the process, as the train must actually be able to go well beyond this nominal speed.
Some tests call for us to go at 320 plus 10%. The train will drive at more than 350 kilometers per hour to ensure that once it's in service, it has enough margin for error to be able to carry passengers safely.
The new TGV is technically capable of travelling even faster than 350 kilometers per hour. But that argument is primarily for export, because in France and the cross-border areas, its maximum speed will be limited to 320 kilometers per hour.
We could travel at 350 or 360 kilometers per hour, but it would only save us a few minutes. However, the increased costs in terms of wear on the infrastructure and the trains themselves would throw off the whole economic model. In Europe, the overall trend isn't towards faster travel, but rather improving the energy impact and carbon footprint of high-speed trains.
Given the climate change challenges and the current energy crisis, the TGV-M holds a lot of appeal for the international market. It also has another major economic benefit that gives it an edge over the competition, a drastic reduction in maintenance costs, largely due to predictive maintenance.
Our goal is to be able to anticipate problems. Predictive maintenance is a major innovation compared to our old TGVs.
The SNCF's first maintenance centre to be adapted for this new model is located outside Paris. It's known as the Southeast European Technicentre.
The Technicentre is where we handle fairly short maintenance operations that last from a few hours up to a week. There are 4 Technicentres for TGVs in Paris. The Southeast European Technicentre, where we are now, is the pioneer. It was the first Technicentre to work on TGVs in 1981. So history is kind of repeating itself, because once again, it will be the first Technicentre to welcome the new TGV-M.
The warehouse is still undergoing transformation as it welcomes one of the TGV-M test trains for the first time. The renovations of the Technicentre will take 5 years and cost a total of 280 million euros.
Nothing had been invested in it for 40 years, so first we needed to do some general renovations and adapt it for the more ergonomic working conditions of today. But of course, we're also making some specific changes just for the TGV-M.
These changes are necessary because of certain modifications to the structure of the train, such as the addition of the graft and the new location of the transformer.
On the roof, the bridge is now 4 meters high instead of 3.5 in order to leave more space for the windows. On the TGV-M, the windows are put in place from the outside, which is more practical than installing them from the inside.
They also had to create an opening on that bridge with a sliding platform in case they needed to work on the new part known as the graft. And that's not all.
The transformers will now be put in place from the bottom rather than the top. So we're going to build a jack that's usually used to put all the axle trees in place on our TGVs.
On the most heavily trafficked TGV line, in addition to the Southeast European Technicentre, the Lyon-Gerland Technicentre and the maintenance stations in Marseille and Nice will also be affected by this initial phase of renovations. Over time, all Technicentres connected to a Parisian station will be transformed, but the SNCF hopes that the TGV-Ms will spend much less time being repaired than the TGV duplexes.
Our goal is to reduce maintenance costs by 30% compared to one of our current TGV trains over the course of the TGV-M's lifetime, which we estimate at 30 years.
Until now, pieces of the TGV would be replaced either after breaking down or becoming faulty, or at regular intervals to head off potential problems, which is called preventive maintenance. This has a considerable impact because it means immobilizing a train that didn't necessarily need to be taken out of commission, or replacing parts that could have been left in place for longer.
The maintenance of the TGV-M is a complete break with what we've done in the past. What we do these days is very repetitive and systematic. In the future, we'll do maintenance as needed.
The TGV-M marks the beginning of a new era for the SNCF, moving from preventive to predictive maintenance. They no longer have a set lifetime for a given piece of equipment. Instead, there are sensors that monitor each part.
There are sensors all over the train, on the air conditioning system, in the air compressors, and in the bathrooms, even the passenger seats. We're monitoring every single part of the train.
Several hundred parts are hooked up to sensors that are constantly taking measurements and sending data. Part of that data is stored inside the train, while the rest is analyzed directly by an artificial intelligence that handles up to 500 variables and can issue alerts to the conductor in real time.
For example, we have real-time monitoring of the temperature in the cars and of any issues with the bathrooms, plus a number of services that are essential for our clients.
Some data can easily be interpreted on board, but the more complex functions of many other pieces of equipment must be compared to other TGV-Ms in circulation. That's why 25,000 variables are transmitted to a central computer every 100 milliseconds.
This data is sent to communication modules that pass through antennas on the roof and use 4G, then 5G to send some of the data back to the servers on the ground.
On the ground, in their maintenance centers, another artificial intelligence will interpret all of the data collected from the entire fleet of TGV-Ms. This way, it'll be able to detect any problems in their early stages, predict if a part is reaching end of life before it breaks down, and enable teams to intervene in advance.
Predictive maintenance will be used to cut maintenance costs. The other benefit is that it will allow us to have more TGVs in circulation at any given moment in time, because we'll be able to anticipate any problem. So we'll have fewer unexpected incidences in the network.
Eurostar. From the UK to the continent, this extraordinary rail link has been revolutionizing European transport for the last 30 years. Nearly 10 million passengers use the service every year, taking advantage of an iconic feat of engineering that opened in 1994, the Channel Tunnel.
It was an historic moment, not just for the rail industry, but also the travel industry as a whole.
It was a first, a 50-kilometer rail tunnel crossing a sea, 75 meters below the surface. With a train every 4 minutes, Eurostar is now the busiest railway in the world.
Departing on time for a Eurostar is more crucial than for most other trains.
From London to Amsterdam, Paris, Brussels, and Cologne, Eurostar is Europe's leading rail network. But running smoothly through 5 countries demands meticulous planning and coordination.
9059, all radio users, doors closing, 9059.
How do you make all the cogs and wheels of an international railway work in unison? How do you guarantee the smooth operation of a link as critical as the Channel Tunnel? How do you orchestrate one of the world's most complex rail systems on a day-to-day basis? Onboard staff, engineers, technicians, we head behind the scenes to meet the experts who keep this crucial lifeline running. Europe's premier rail network, the Eurostar. England, France, Belgium, Netherlands, Germany. In 3 decades, Eurostar has established itself as a major network, an essential link between the major cities of Northern Europe.
We can have up to 6 or 8 trains running at the same time on different routes. For example, trains arriving from London while trains are leaving Paris, departing from Brussels with others setting off from Amsterdam.
Eurostar connects the continent. Right from the outset, this line was inevitably going to be one of the most complex in the world. As well as needing to be operational across different rail networks, it first had to solve the major problem of crossing the sea. The starting point for this ambitious undertaking, then, was a key undertaking, a veritable feat of civil engineering. And without it, nothing else would have been possible: the Channel Tunnel. A visionary idea that had been around for decades, centuries even, was finally given the green light in 1986. And in 1987, the work finally began. 1,200 workers, engineers, geologists, and technicians set out to conquer land and sea. To finally realize this ambition, a tunnel had to be dug beneath 35 meters of water and 40 meters of rock. an undertaking that required some extremely powerful tunnel boring machines. Using 11 in all, they were tasked with digging not 1, but 3 tunnels simultaneously. Underground conditions for the work teams were extreme, given the huge pressure exerted by the English Channel and the seabed, which is 10 times the Earth's atmospheric pressure. During digging, the rock ceiling overhead could collapse at any moment. To avoid such a tragedy, the tunnel structure had to be put in place immediately. Meter by meter, the tunnel boring machines laid the concrete elements that would support the entire structure. Meanwhile, 4 pumping stations were set up to cope with the constant seepage of water from the seabed. After only 6 years of digging, the work was completed on May 6, 1994. 10 million tons of material excavated, 1 million tons of concrete laid. A total of 50.5 kilometers, 38 of them beneath the English Channel. To this day, it remains the world's largest underwater tunnel.
The design of the Channel Tunnel is just extraordinary. It's so sturdy in terms of the safety coefficients. The more you look at it, the more it seems indestructible.
In June 1994, the Channel Tunnel was finally open to traffic, and the first cross-channel railway link appeared. The Eurostar was born.
The fact that you could go from London to Paris direct on a train through a tunnel was absolutely huge.
Right from the start, the Channel Tunnel was a great idea. Imagine trains traveling at 300 kilometers per hour on land and 160 kilometers per hour, 75 meters underwater for 13 minutes.
Since it came into being, the trains on the network have been in a constant state of evolution. In 30 years, they have enabled 200 million passengers to cross Europe at high speed on both sides of the channel. Whereas previous land-sea links between London and the continent were laborious, with air travel the only rapid solution, the Eurostar line with its tunnel has created a direct link between the heart of Europe's major cities. In England, the day begins at London St Pancras Station. In London, 1.5 hours before departure, train 9022 is all set, standing ready for service under the magnificent glass roof of this historic station. Here, an entire floor has been dedicated to the Continental Link.
Good afternoon. We are very pleased to inform you train 9132.
On site, the local teams ensure that everything is perfect for train 9022.
Excellent news. Thank you very much.
TD Paris.
Thank you. Bye-bye.
Preparations are made for boarding. Half an hour later, 1 hour before departure, Kevin, the driver, takes over. His first task is to check his work tool down to the last detail. The train's exterior, of course, but above all, its steering and safety instruments.
To prepare the train, the first thing we have to check the outside, make sure that the lights are working, that the nose cone is closed. Then we come into the cab, we have to check that we've got all of the safety equipment available in case of emergencies, and then we have to check all of the braking systems and the safety systems that they're all working.
Backward emergency brake.
It's working well. All tests in the cab are complete. Everything is satisfactory. Over.
Departure for Paris is now only minutes away. The driver keeps his eyes glued to the signs. In just a few moments, he will be authorized to set off along the tracks.
Green. People are down.
At 12:04, Kevin sets Eurostar 9022 in motion. The train glides through the London suburbs along the English rail network, which required major changes to accommodate the high-speed rail link between Paris and London, which now takes just 2 hours and 17 minutes. Along the way, the driver's attention is put to the test. Focusing on the track and its control screens, one of his main jobs is to make sure the train has enough power at all times.
The train has a maximum speed of 300 kilometers per hour, which is a very high speed. And in order to power that, it takes 25,000 volts through the overhead power cables. But also the systems of electricity are different in different areas. So we have to change electrical systems at different points in the journey.
As they cross Europe, Eurostar trains operate on numerous rail networks. Different countries have different infrastructures, with variations in the power supply, which ranges from 15,000 to 25,000 volts, for example. The pantographs on the roof of the train collect this electrical energy throughout the journey. They are in contact with the catenary, the electrical cable that runs along the entire line. But every change in voltage requires a new pantograph. Some need to be lowered and others raised to maintain the train's power supply. Time is of the essence. These changes have to be made at precise interconnection points to avoid damaging the entire line. Not too early, not too late.
That is a critical moment when driving the train, because if something distracted you and you selected the wrong system, that could cause problems, like it could potentially break the power cables, and then all the trains would have to stop. So that's the moment when you have to be really concentrating on what you're doing.
After racing through the suburbs of London and the countryside of southern England, train 9022 is approaching a critical point on its route: the Channel Tunnel.
And here is the tunnel entrance. We are exactly on time at the tunnel entrance, to the second.
The Eurostar leaves the British rail network and enters the tunnel. Once inside, it is entirely dependent on the tunnel's power supply, as Eurotunnel has its own independent electrical network. Power management is one of the greatest challenges facing underground infrastructure, and one that carries a huge responsibility. The Eurotunnel must be able to provide a seamless power supply to the hundreds of trains that pass through it every day. At maximum capacity, as many as 16 trains can be running simultaneously 75 meters below sea level. A power failure would spell disaster. To that end, there are 2 sets of catenaries supplying the 25,000 volts needed for traction to enable maintenance at any time, and they can be powered from either the French or the English side. Voltage is also monitored throughout the tunnel and can be rebalanced in real time to ensure that there is sufficient power for the trains running underground.
Our primary objective, one we've done a lot of work on in recent years, is to provide these trains with a power supply of such quality that they will experience a virtually zero failure rate when crossing the Channel Tunnel.
It's a huge challenge, and to meet it, the Channel Tunnel boasts a wide array of equipment that is as powerful as it is complex. High-tech devices capable of compensating for voltage variations in real time, and robust power supply systems able to withstand the highest energy levels. Of all the installations, the most critical are without question the substations responsible for collecting electricity directly from the national grids. Standing at the tunnel entrance, the French substation is the main source of power for the entire structure.
The whole Eurotunnel grid starts here. This substation is the base for the catenary network powering the trains. It's vital. Without it, we're limited as to how many trains we can run.
while their primary task is collecting electricity. The substations must also transform it into a usable form, from 225,000 to 25,000 volts, and inject it into the structure's circuits.
Switching to local?
To ensure the reliability of the installation, the whole system is checked regularly, in its entirety. And it's a delicate operation.
Leaving ARS and CN concordance.
The power has to be cut on the French side, while the English station takes over. The Eurotunnel is the perfect embodiment of cooperation between the UK and the continent. Everyone is in sync to maintain continuity of service inside the tunnel. On site, the teams disconnect and physically neutralize the installations. Tens of thousands of volts race overhead. Once grounded, they can continue their inspection and see if anything needs attention. The slightest defect on a mechanism, the slightest trace of corrosion, the tiniest alteration to a cable, nothing is left to chance.
We're here every week on Thursday mornings. There's a complete check of the network and substation. We carry out maintenance operations in this substation all the year round.
This vigilance is crucial to ensure a smooth journey for trains traveling under the channel. But it's especially important as the station supplies all the tunnel's electrical installations, as well as the catenaries. Around the historic structure, a whole range of systems and infrastructures are incorporated into the network, including the huge rail and road terminal serving the tunnel entrance, the traffic control center with its countless sensors, and the signaling systems in operation throughout the crossing to keep drivers informed. Last but not least, the network powers the safety devices required for the underground crossing, like the gigantic ventilation system that makes the structure viable.
Ventilation is what makes it possible to breathe in the Channel Tunnel. By definition, a 50-kilometer tunnel is an inert zone. So if you don't ventilate it, you can't stay alive in the tunnel.
In order to circulate fresh, healthy air throughout the entire structure, the Eurotunnel is equipped with a veritable aeration plant. This installation is capable of cooling air and blowing it out at a rate of 100 cubic meters per second, the volume of 2 Olympic swimming pools every minute, and circulating it underground. This constantly renewed air supply is particularly important in one of the key sections of the structure, the service tunnel, accessed by crews on a daily basis. The Sangat shaft, the Eurotunnel's historic starting point, is one of the main entry points for the service tunnel. Right at the bottom, a highly secure access corridor leads to an underground airlock system. Injected air is maintained at a slightly higher pressure. This is an important feature, as we will see. Once through the airlock, maintenance teams finally enter the service tunnel. This tunnel, 4 meters in diameter and positioned between the 2 main tracks, runs the full length of the structure. It is dotted with equipment rooms, piping, and communication systems, as well as connecting areas providing access to the rail tunnels. Most importantly, thanks to this corridor, maintenance and safety teams can intervene rapidly at any point within the structure. Using small, custom-built vehicles, the technicians are constantly on the move.
Yes, no problem. We'll head back to the France portal.
All along the 50-kilometer stretch, every piece of equipment has to be regularly checked. Every light, door, and service telephone.
Yes, it's Julian. Can you hear me? Okay, thanks.
The service tunnel is the subject of so much attention because, as well as being a maintenance tool, it's also the main safety facility for the entire structure in the event of an accident. Every type of incident, from a simple breakdown to a potential worst-case scenario, needs to be dealt with.
There are certain systems which have to be working, which it could be okay for the train to operate on a normal network in the UK or in France. If certain things are not working on the train, it might not be able to go into the Channel Tunnel. So it has to meet those minimum standards.
In the event of an unexpected stoppage, or worse, a fire, the tunnel needs to be evacuated quickly, very quickly. For a Eurostar train, that means bringing no fewer than 900 people to safety from a point somewhere between France and England, 70 meters underground, and beneath the sea. To that end, the tunnels have cross-passage access points built into them, allowing passengers to take refuge directly in the service tunnel. They are spaced every 375 meters, which is why Eurostar trains are 400 meters long. That way they are sure to stop in front of at least one access point. This is when the slightly higher air pressure in the service tunnel applied by the ventilation system comes into play. In the event of a fire, when the access doors are opened, the pressure differential will prevent fumes from entering the service tunnel from the railway tunnel.
In the service tunnel, passengers are immediately in a refuge that is completely safe. Thanks to the Channel Tunnel's complex ventilation system, conditions for evacuated passengers will be wholly normal.
At the same time, the ventilation plant on the surface has the capacity to increase its blowing power threefold, up to almost 300 cubic meters per second, should it need to purge fumes generated by an incident in the railway tunnel. Safety systems, power supply management, constant maintenance operations, and rail traffic organization. These challenges are met on a daily basis and allow the Channel Tunnel to handle a world record 400 trains a day.
We're now approaching the exit of the tunnel, about to enter into France.
As Eurostar 9022 emerges on the French side, it is preparing for a return to its cruising speed across the continental countryside. The driver accelerates, gradually increasing his speed from the 160 kilometers an hour limit allowed in the tunnel to the 300 kilometers an hour his locomotive is capable of. However, it is not about accelerating hard to hit maximum speed as soon as possible. Train drivers need to be constantly aware of the constraints around them, such as visibility issues, track conditions, potential dangers, or unseen events in the vicinity.
And this is part of the line where we can do our top speed of 300. Safety is the most important part of driving the train, because we need to be able to stop the train quickly and safely in case of any emergency.
The driver, then, is responsible for this fine-tuned speed management, an undertaking determined by complex lane markings, read and interpreted by the train itself. It's one of the special features of Eurostars. Signaling depends on the type of line and the country. Information is sometimes transmitted via beacons directly on the line, sometimes transmitted remotely and received by antenna on the train. In other cases, the speed is directly controlled by the infrastructure itself. Eurostar's trains need to incorporate all these systems if they are to cross Europe in complete safety. Along the way, the driver has to maintain his focus, both on the track and on his screens.
Speed restriction coming up ahead.
On the approach to Paris, as the landscape becomes denser again, the train slows down. Through perfect speed management, the driver manages to stay on schedule. He pulls into the Gare du Nord right on time. It's a daily feat taken for granted by passengers, but essential to the complex management of the cross-channel link.
And we have arrived.
Since its launch in 1994, the Eurostar service has become a fixture in the heart of Europe's major capitals: London, Brussels, Amsterdam. Cities whose historic infrastructures have had to adapt to the arrival of this new type of line. An international train crossing Europe all the way to the UK. All this while making sure that the countries concerned can control and manage the new border crossings. In Paris, Gare du Nord was the logical choice for the cross-channel line. But then, it has to fit in with the daily hustle and bustle of the famous station.
The first Gare du Nord was built in 1846, and back then, stations were just landing stages, so there weren't many services. Since 1846, the Gare du Nord has continued to adapt to changing traffic flows and needs. In 1864, the station was rebuilt, and since then it has been enlarged and redeveloped.
Over its 170-year history, the Gare du Nord has seen all the developments and evolution of railways and public transport.
Today, the Gare du Nord handles 700,000 passengers a day. And that's where the challenge lies. We have to be able to provide services for international travelers who don't necessarily speak French, who may not even know Paris, while meeting the needs of commuters who live very close to Paris, or travelers who are just passing through. So these two groups of people need to be managed within the same station.
From its original 2 single tracks, the building has expanded to include 15 platforms, serving a network with increasingly complex switches. But this is just the tip of the iceberg. The station extends underground on 3 levels. The first 2 service platforms, handling passenger flow and directing them to the 3rd underground level, where 3 RER lines and 2 metro lines can be accessed, with a dozen additional tracks plunging to a depth of 30 meters. Today, it is the busiest station in Europe. The challenge was to integrate Eurostar into this incredibly complex mix, with all the rigmarole of managing international connections.
So when the Eurostar arrived, it brought with it a new factor, the aspect of crossing borders. In a virtual sense, passengers actually enter the UK at the Gare du Nord, or at least find themselves in a zone somewhere between France and England. And that's what inspired the current layout. The idea was to introduce a kind of sterilization, to create a hermetically sealed box for people and goods.
Within the station, the 4 westernmost tracks have been exclusively allocated to the cross-channel line. Around them, a so-called sterile zone has been created with a physical and inviolable separation of the tracks along the entire length of the platforms. Above is the overhanging mezzanine, where border crossings and boarding are organized as efficiently as possible in the style of an airport terminal.
The issue of Eurostar stations is absolutely fundamental. Today, when you're in London or Paris, I don't think there's any other place in Europe where you can cross the border in such a short space of time. Here in Paris, you go past the border police, leave France, take 3 steps, and then enter the UK through the UKBF, UK Border Force. So obviously, these are border crossing points which are absolutely key for us and immensely complex places to run.
Every day, at the rate of more than 1 train an hour, Eurostar crews carry more than 30,000 people across the UK border into the heart of Paris. Paris, Gare du Nord station, 5 o'clock p.m. Eurostar train 9022 from London is arriving. The passengers have disembarked, and the train, now renamed 9047, must begin preparations for a new journey in the opposite direction. For the teams on site, the countdown has begun. They have 1 hour to organize the next departure.
Coach 10, there is a ramp with a companion, and coach 14 is a wheelchair assistance, just so you're all aware.
Cleaning the train, loading meals, welcoming passengers. As train manager, Blake is the link between the passengers and the entire Eurostar team.
You good?
All good?
Yeah?
Good, yeah?
Yeah, everything okay with the train?
All good. Well, actually, we have an issue.
He's in charge of making everyone feel welcome and comfortable, but like the driver, he is above all responsible for the train's safety and reliability throughout the journey. As soon as the train pulls in, the train's manager's first task is of paramount importance. He reviews the entire train, starting with its exterior.
We start when the train arrives in the platform, even though it might have travelled already from London to Paris or from Paris to London. We start as a blank sheet of paper, so to speak, so we check the train entirely from top to bottom before it goes out on its next journey. So for us as train managers, we'll start by looking at the exterior of the train. We're checking that none of the windows have been broken during the journey. It's a 400-metre long train, so that takes a bit of time. We're also making sure that all of the parts underneath the train, there are some cupboards and electrical compartments underneath the train, we're making sure that they're still correctly in place.
A Eurostar is made up of 16 carriages in a single section. At almost half a kilometre long, it is one of the largest passenger trains in the world. Hurtling along at 300 kilometers an hour, the train is subject to the usual dangers associated with extremely high speeds. The slightest impact can shatter a fragile part of the bodywork. The train also has to cope with the effects of bad weather so common in Northern Europe, and amplified by speed. Every part must be positioned correctly to absorb the slightest vibration. These monitoring points are the daily lot of high-speed professionals. But when it comes to crossing the sea, the Eurostar's real raison d'etre, the train faces some unique challenges of a type never before seen in the world of rail travel, the ones introduced by the Channel Tunnel.
Safety is a crucial part of any railway, especially for us, of course. We have 2 elements that are different to some other railways that people might have travelled on before. Of course, we have our speed. We're travelling at speeds of up to 300 kilometres an hour. And then, of course, we have the element where we are, at one point during our journey, some 75 metres beneath the surface of the sea. Those 2 elements are always going to necessitate an extra care.
With its exceptional depth and length, the tunnel creates what is known as a thermal inertia zone. The temperature is around 15 degrees Celsius at all times, summer and winter. As a result, during hot or cold spells, the nature of the infrastructure subjects the trains to temperature differentials that can sometimes reach several tens of degrees. These variations place unusually high demands on the machine's parts and gears. While the crews are busy checking the train down to the last detail, departure time is approaching. In 20 minutes, passengers will be rushing to the platforms. And 46 minutes from now, train 9047 will be heading for the UK capital. There's not a moment to lose, especially as the train manager's attention must now turn to a key element, the powertrain.
If you were running just in the normal countryside in France, in the UK, Belgium, in the Netherlands, that you had a reduced amount of power available to you would be an inconvenience. It would slow you down, it would have an impact on the timetable, but it wouldn't necessarily be a safety issue. As soon as you're putting a train with potentially up to 900 people in a tunnel underneath the sea, it becomes a very different situation.
Whenever one of the Eurostar's 32 engines fails, the crew must ensure that the malfunction is isolated. Because if more than half the engines become affected during a journey, then taking the train into the tunnel and risking a breakdown in the middle of the English Channel is out of the question.
We have to be sure that our train is going to be capable of completing the journey through the tunnel. And that might mean that even in the case of something else happening, let's say in the worst case a fire or an incident with the train, that the train is still capable of removing itself from the tunnel.
Such thoroughness, along with the need to plan for the worst-case scenario, is a legacy of the unique nature of the line and its central infrastructure. The safety of all passengers is at stake. This requirement even extends to equipment inside the train.
So for the safety on the inside of the train, we need to check that the alarm systems are working, the red handles that everyone's used to seeing on trains, we need to make sure they're functioning correctly. We need to make sure that the air ventilation system is working correctly. That's an essential part of people's safety on board. TM1 for TM2, are you receiving? Over.
TM2 receiving.
Yeah, all good for the PIDs on the front half, over.
Everything is in order. In just a few minutes, no fewer than 900 people will be boarding a train ready for departure, while passengers are already checking in for the following train.
Okay everyone, TM1 speaking, just to advise you, boarding starting shortly, boarding starting shortly. We've been practicing for nearly 30 years now how to do it. And with experience, we've learned how you can load up to 900 people on a train and do it quickly but safely. Everything that we do in terms of boarding is timed down to the minute. For example, I'm required to start the boarding some 26 minutes prior to departure time. Not 25, not 30, 26, because we've worked out that's how long it takes. And we know that after about 22 minutes, we should have everybody on board. That gives us enough time to deal with any minor issues as well. Mesdames, Messieurs, chers passagers, j'ai le plaisir de vous informer que l'embarquement de notre Eurostar est terminé. Nous allons bientôt fermer les portes d'accès. Pour votre sécurité, veuillez vous éloigner des portes d'accès qui seront fermées automatiquement. À très bientôt.
Everything under control. Eurostar 9047 can finally get underway. In just 2 hours and 17 minutes, it will pull into the UK capital. Gradually, the train accelerates and leaves the Paris region. At kilometer 67, it reaches cruising speed, approaching 300 kilometers per hour. Once on its way, departure schedules and timetables must be meticulously adhered to. A train is never alone on its line. On the contrary, it shares it with numerous other connections running along the same rails, only a few minutes apart.
A lot of people, I think, understand with aircraft that aircraft fly to a slot, that they have a departure slot from the airport and they have an arrival slot to respect at the destination. So it's quite similar with railways. The timetables are all written, the trains should fall into their specific part of the timetable. If we don't fall into that specific part of the timetable, we can end up behind a slower train, or we can end up behind a train that's stopping in a station that we don't stop at, and that can cause us delays going forward.
For the Eurostar, keeping to schedule is all the more crucial as it leaves Paris on the busiest high-speed line in Europe, the LGV Nord. Over its 225 kilometers, no less than 30 trains run every hour. These include Eurostars and many other high-speed trains. The slightest hiccup can have consequences for the rest of the day's journeys right through the network. This record-breaking ridership calls for a great deal of fine-tuning and, most importantly, the ability to adapt in real time and on a Europe-wide scale. The impact of a passenger problem in, say, Amsterdam Station needs to be assessed in terms of the consequences for a train running 2 hours later through high-speed traffic in northern France. All this in the knowledge that the slightest error can translate into increased delays for all rail traffic on the continent.
Sur la rame 3205-3206, on a une IMO chez vous cette nuit. J'ai pas la possibilité de l'assurer.
To achieve this, Eurostar is equipped with a control center that can precisely track each of its trains in any territory in its network.
It's the control room's job to closely monitor what's going on at all times. It knows exactly where each train is, where each train manager is, and each driver is committed to ensuring that everything runs smoothly. So it's their job to coordinate all these trains with one another right across these networks.
Here, using the tools at their disposal, the teams can centralize all the geographical, timing, and forecast data for the networks in each country. They keep an eye on all the rail traffic in France, the Netherlands, Belgium, Germany, England, even under the sea.
We've created an in-house map in which we track all our GPS-based traffic, plus ground data, so that we can actually see the speed of the train, where it is, what it's doing, and how it's going. Then, if there's an incident on, say, the French network, we use the tools linked to the French infrastructure. We then pinpoint it, see whether there are trains ahead or trains behind, because it's important to be on top of developments and decide how we're going to handle a situation and how it will pan out.
Donc je peux appeler de la zone de contrôle. Donc on fait 43 pour 152.
The operators are in direct contact with each crew, as well as with the other European rail companies and the managers of the various rail networks used by Eurostar. In the event of an incident or unexpected breakdown, whether a Eurostar train or otherwise, the control room is able to identify a series of alternative escape routes and determine the optimum way to bypass the incident, even if it means temporarily leaving a high-speed line and rejoining it later. Other companies using the same track are then alerted in order to prevent a domino effect, whereby the incident impacts the entire network. In this way, a potentially dangerous disruption is restricted to just a few minutes delay.
I've got a small change to tell you.
It's not just us. We're in the middle of all the other traffic. So anything we do has an impact on other operators. But all the things they're dealing with also have an impact on us. So that's our job. We have to work in conjunction with them to be as efficient as possible.
The objective is clear. Know everything, anticipate everything, control everything. It's a rule that becomes all the more crucial when it comes to the key infrastructure of the route, the Channel Tunnel. In northern France, on the approach to Calais, train 9047 lowers its speed. This now historic section of track linking the UK to the continent is the most critical point on the Eurostar route. This piece of infrastructure is at the very heart of all the timetabling and dictates the scheduling of departures from stations right across Europe. The 50.5-kilometer structure running deep beneath the English Channel is actually made up of 3 tunnels, a service gallery, and 2 railway tracks, one for each direction of traffic. This configuration allows almost 50 Eurostars to run through it daily, as long as a strict schedule is adhered to. Each train has to commit to a given speed for a very precise length of time.
The tunnel gives us a timetable, Then we have to get to the tunnel, which is the bottleneck. Whatever else you do, you have no choice. You can't get to England without going through the tunnel, and it's one way up and one way down. We really have to fit in with their rhythm and do it their way to get it right and be efficient. So a lot of work is done upstream to keep things moving.
The tunnel is a real funnel. All the more so as the Eurostar is not the only service to use this unique link between France and England. The infrastructure managed by Eurotunnel, an independent company, is also used by freight trains and shuttles carrying trucks and cars. Around the underground structure, the company has developed an impressive boarding terminal. Every day, more than 4,000 trucks and 6,000 private vehicles pass through the tunnel.
Bye-bye.
They are directed to the platforms before boarding huge 800-meter-long shuttles.
Hello, may I have a look? Thank you. Oh, okay, thank you very much.
Once on board, after some final safety checks, they are ready to head off under the channel with the rest of the rail traffic. Shuttles, freight trains, and Eurostar all run on the same tracks and under the same sea. With a train every 4 minutes, the tunnel is now the busiest rail infrastructure in the world.
F5, I have one stopped. Yeah, we can put it on F5, let's do it.
To coordinate all this traffic, the tunnel operators naturally have their own control room, quite separate from the one used by Eurostar. Using an impressive bank of screens, the teams can keep an eye on the tiniest details and monitor any movement within the structure.
There are lots of different users. We have a daily schedule that we have to stick to closely. And with a departure every 4 minutes, it's really tight. The slightest delay can have a knock-on effect on other traffic leaving from France or England.
Laurent, the transfer's ready. Can I send it right away?
Yes, you can go.
Let's do it.
Added to the sustained rate of departures is another complicating factor, which is that the trains travel at different speeds while actually in the tunnel. For freight trains, it's around 100 kilometers an hour. For the Eurotunnel shuttles, 140 kilometers an hour, and for Eurostars, 160 kilometers an hour, which are restricted for safety reasons. As the day progresses, they need to be released into the tunnel in the right order so that the slower ones don't slow down the faster ones.
Eurotunnel trains run at 140, and Eurostar passenger trains at 160, meaning a fast Eurostar will catch up to one of our trains over a distance of 50 kilometers. So it's up to us to optimize the Eurostar's entry so as not to slow it down in the tunnel. To that end, we may have to hold back one of our trains for a minute or two to enable the Eurostar to hit 160.
Any unforeseen event requires immediate action and constant communication with the Eurostar teams to avoid accumulating delays.
Hello, it's Veronica Thierry. How are you?
On the operational side, our job in the control room is to notify Eurotunnel the moment there's the slightest disruption, and to alert them that we're breaking with the schedule so we can fill any remaining slots and make sure as little time as possible is lost.
We need to adapt constantly, and it's very time-consuming. In fact, as you see, we're in regular contact, so the phone rings a lot. Yes, go ahead.
With the incessant flow of trains through the tunnel, the traffic control centers guarantee the safety and fluidity of this crucial link 24/7. After its journey beneath the sea, train 9047 finally lands on British soil. Just a few dozen minutes later, it pulls into the heart of London at St. Pancras Station, the terminus. Here, on the platforms of London Station, the passengers alight and the train empties. Blake, the train manager, brings up the rear before calling it a day.
We take great pride in our trains as train managers. We consider them like our homes, really, and when we have people on board, it's like they're coming to visit us at home. So you look after them. You look after them from the point they arrive until the point they leave.
After a smooth ride, timed to the minute, the hustle and bustle subsides. For train 9047, the daily shift is done. Over the past 30 years, the Eurostar network has expanded throughout Europe. Considering the line that had so many special features when first created, it was always destined to be one of the most complex in the world.
Obviously, many technological and infrastructure difficulties had to be overcome to create this line and put the trains into service.
Over the years, the network has expanded. After the UK, France, and Belgium, this now essential link connects the Netherlands and Germany.
Europeans can live in Paris, study or work in London, come to see their parents in Paris at weekends. So yes, it really has changed people's lives.
You can't say that that's just a train. That's much more than a train. That's a change in political and social life in an entire continent.
The excitement and the romance of that has continued for nearly 30 years. So, you know, we're so lucky that we can be part of that. People's travel behaviours are changing, and they're changing to a green mode of transport. That's what Eurostar can provide and has provided for nearly 30 years.
Today, the Eurostar punctuates the daily lives of millions of Europeans. It has redrawn the contours of the continent beyond its seas and its borders.